Queso here.
Go ahead.
Hey, it's Queso. Sorry I'm taking up like the whole screen. Lex did not write 5.3 exponential functions down in time. So yeah, 5.3 exponential functions. Ciao.
Jack, I forgot to hit record. Can you do it again? Just kidding. I do. All right. Shh. Hush now. Everybody get the sound. Because I'm going to end. I'm going to take this off. Now listen, it's going to be a little bit different today. A little bit crazy. Usually I have my little slidey slides out where we go through the examples and we do the try-its. We'll save that for tomorrow. Today I'm going to play a little video. I know it sounds exciting. It's a math video.
Don't make it strange.
It's only 3 minutes long, not even. It's 2 minutes and 40 seconds. And it's going to it's going to kind of bridge the gap. Because today we're talking about exponential functions, we just had like, has it been, like 3 weeks or so just on exponents and all the properties of exponents and the rules and the regulations and things like that, right? Yeah. And it's been tough. And now we're going to apply everything that we know to functions. Exactly. So the good news is it's not going to get it's not like we have to remember every single complicated, crazy thing that just happened for these functions, but there are going to be some of those properties that are going to carry over, and we do need them in order to understand and process through functions. Now, she asked a really good question. She said, what's a function again? How can we describe a function in one word? It starts with an M.
Math.
Multiplication.
Muffin. I think I know.
What?
Multiplication.
Nope. It's not a math word.
Oh.
Monopoly.
No.
Oh.
It starts with an M.
McDonald's.
It's a machine.
A
A function is a machine.
A machine?
A machine.
Machine.
It's like it's an imaginary machine. Okay. That's right. She remembers. She remembers why I call it a machine. Because if you picture like, I don't know, picture like an old cartoon or something where like the mad. Why are you talking while I'm talking? Where the mad scientist invents this like crazy machine. What's the first thing he has to do to the machine? He has to put something in, right? He puts something in, and it goes like, it starts like moving things around, like smoking and bubbling and everything like that, and then he waits for something to come out. Something goes in, the machine does something, a function. The machine has some sort of function that it has to do, and then whatever came in had to go through that function, and then the machine puts something out. You put something in called the input, also known as x. The function does its functioning thing, and then it spits out the output, which we also know as y. Very good. Now, quick thing. Remember that an equation and a function are really the same thing. But one is just written with this weird f and the parentheses and the x, and it's like, why is it doing that? Are f and x being multiplied? What's going on? No. It's just a different way of writing. So let's just, you can write this down because this is actually helpful. Let's just take our good old friend, a linear equation. Let's just try like y equals 3x plus 2. A good old linear equation in slope-intercept form. If I write it like this, what's changed about it? Has the machine changed?
No.
No. Has anything about this changed?
Nope. No.
If I graph both of these, will they look different? No. So the only thing that's changed is the way that I wrote it. That's why we call it notation. Function notation. Notation coming from the word note, or notate, right? Writing something. It's just the way that we write it. And you might be thinking, well then, why do we even have that then? If they both mean the same thing, why can't we just always use y? Anybody know? Yes.
Because that one goes through specific output.
What's that?
Right. It goes in a specific way. Like f of x, like it goes to x, not like g.
I think you're on the right track, but pause that thought for a second, yeah.
Depending on the question, it might be easier to find the x.
Anybody else?
No, wait. First you do the x2 and x1.
Yeah?
Like, doesn't the machine like look like this?
Well, that's not helpful right now. Well, I like all these thoughts. Let me steer you in the direction, okay? What?
We put a number in the x in the parentheses. We solve for that.
Yeah, but those are not, it's not that what you guys are saying isn't true. It's just not quite answering the question that I asked. So it's okay, we're just like brainstorming here. So what I asked was, why, if this does the same thing as this, why would we have this? It looks more complicated. I don't like it. So why do we need it? Remember that when we write in function notation, it's not always f of x. Sometimes we write it as g of x or h of x. So now we're getting super complicated. Why are we using all these letters of the alphabet? Why would we do that?
Because like there's can be multiple functions in an equation.
Yes, because we need to be able to distinguish between different functions on the same graph, right? Or different pieces of information like if you have a business and you're projecting some sales or salaries or something like that, and you want different ways of writing them, you can use function notation because you can label one f of x, the next one g of x, you could do b of x, z of x. I mean 26 ways, right? There are 26 letters in the alphabet.
Oh wait,
You said, is this what the function machine looks like? That's what you said.
wait.
This.
Oh yeah, wait.
So this function notation is helpful to us.
27 is the Spanish alphabet.
Yeah, because of the n. Okay. Or the, okay, obvious.
No, it's an
Yeah,
N.
it's
Oh, it's
27.
n. Anyway, all this to say, the first thing that we're gonna do is we're going to watch a little video that's going to remind us of our good old friend, the linear equation, or linear function, whichever way you wanna call it, okay? Right now we're just working with equations, we're just working with x and y, but just keep in mind that f of x would be the exact same thing, and you'll see a lot of f of x in this lesson. But for now, we're gonna watch a video that's gonna show the linear equation compared to the exponential equation. Now, before I play the video, look at this, isn't this crazy? The x is the exponent. The x is the exponent. It's pretty cool, right? But it is weird though, because we know that as the graph moves along the x-axis, the x value changes, so the exponent is the variable. The exponent is the variable, it's going to change. Never mind. You're zoning out. I know, are you okay? All right. Shh. Thanks. Look alive, come on. All right, so it's definitely different looking, right? To see x up in this top corner, this tiny little x. We're so used to seeing it right next to this. It's like, that's the slope, I know that. Yeah, it's cool because lines have slopes. Exponential functions, not so much. Lines have y-intercepts. Exponential functions also have y-intercepts, but you can't really see it from writing it like that. So there are a lot of like little differences that we'll have to get used to. We're just getting to know our new friend, okay? This is like friends at our old school, and then we go to a new school and we're making new friends and we're like, I don't know you, but it's okay, because I'll probably get to know you and I might like you, and then we'll get to hang out and it'll be okay. But we're very comfortable with our good old friend because he's in slope-intercept form. We know how to graph him. It's easy. This is a little scary looking, but we're going to spend some time getting to know our little exponential function friend today. Yes?
I was looking at a calendar and there was something homework for like this class one day, so I looked at it and it looked like this and I freaked myself out.
Yeah, that's what happens. Don't look at homeworks until we do the lesson. Unless you're the kind of person who can do that and like loves the challenge. If you're the kind of person who freaks out when you see something like that, like that's what I would do too. I would not look ahead unless you like get a thrill from that challenge. But if you get freaked out, just don't do it. Just wait. Okay, I wouldn't even start the homework tonight. I would just take a night and just.
Yes, I love that idea.
Okay.
Good idea.
And then
great
you'll
idea.
have the whole weekend to do the homework.
Awesome.
I'll also have a homework video up tomorrow. Okay, wait.
What?
Yes, I'll have a homework video up tomorrow. That is correct. Okay, so we're gonna get back to comparing. This video is really short, but before I start the video, I want you guys to copy this down. And I'll hand out some graph paper.
What's coming? Everything
Why are we talking? And making noise? If you want graph paper, raise your hand. Are you
What?
Anybody graph paper here? You guys have? You need to paper. Graph paper? Anybody?
Me. Me.
Anybody graph paper? Sure. Raise your hand.
I wrote it down.
Oh, you did? It's the tiniest graph I've ever seen.
Yeah.
Could you try to make it a little bit bigger? Zoom in. Yeah, zoom in.
I don't need it.
There. I'm making it bigger over here.
Oh, you don't need it. Anybody else know? Oh, we're still talking?
No.
Even if you finish writing, it doesn't mean it's going to talk.
Can I draw a graph on very little piece of paper? Or does it have to be on graph?
No, it doesn't have to. That's why I asked if you wanted graph paper.
Either way, I got graph.
Oh, it's up to you. However it works best for you.
That's not it. Sorry. Sorry. No, can you just give me like 10 minutes?
Just go like this.
Wait, I need like potions so I can like yeah,
I want to laugh too.
the other person.
No, we went in the line for
Yeah. I'll make it a little bit easier to write down. I'll show you what these points are. So this one is
one. Where's the center?
0, 1. This one is 1, 2. This one is 2, 4. And then going backwards, this one is -1, 1/2. This one is -2, 1/4.
Yeah, you're so
What the?
It's hard to do that. Just do your best. And then the line continues to go down.
I can't even like read my April.
So something that you're probably noticing about this graph, the graph of it's curvy. Yes, the exponential function's got curves, okay? So, it doesn't have that straight line, doesn't have that easy slope where you just know what point's coming next because it just does the same thing over and over, right? It's curving and getting really bendy and funky. Excuse me, sit. Oh gosh. All right, get together. I mean, get it together, not get together. What?
Can you please move so I can see the arrows?
Pointing.
Pretty please. Thank you so much. I deeply appreciate it.
Okay.
Yeah, but I don't.
All right, so you'll notice that the exponential function is curvy. You'll also notice that it looks like, does it look like it's touching the x-axis eventually?
No.
Well, it's not.
It's like very.
It's not. Okay, it wants to. It's trying so hard. Over and over. It keeps trying. Every time the x value moves over to the left, the y value is trying to go down and eventually touch the x-axis. And it can't. Even if we graphed this all the way, because we see that at when x is 0, it's at 1. When x is negative 1, it goes to a half, which is getting closer to 0. When x is negative 2, it goes to a fourth, which is closer to 0. And then it's going to get, the fractions are going to get tinier and tinier and tinier until you have like 1 over like 16 million.
Why is it not
right?
like?
Well, why can't it? I'll put the x-axis.
We'll see it when we got it. It's a good question. I'll explain that in a little bit. But first, because it's trying so hard, even if you picture this graph extending like to the end of the Ovation building, right? So like the end of the dance room, if you picture this graph being drawn, and I don't know what number that would go to, like what, like 50,000 or something like that, right? Maybe not that high, maybe like 10,000, who knows? But let's just say it goes to like 10,000. Even if we were to bring this graph all the way to negative 10,000 on the x, to the naked eye, it would look like it's touching, right? If we were to actually draw this, because it already looks like it's touching. Because it's getting so close. But it will never, ever, ever touch. Now, did anybody notice that really weird looking word in the vocabulary on the side?
Anemone.
No. Did anybody remember what it said?
It was like anemone. Or like
It starts with an A.
Asymptote.
Yep, good.
Cycle.
She wrote it down. That's even better than being able to pronounce it. It's pronounced asymptote.
I saw what?
I got asymptote.
You're putting
Repeat after me. Asymptote.
Acid.
Asymptote.
Anemone.
There's a P in there too. Asymptote. But you don't have to say the P. Asymptote. Asymptote. Say it. Very good. Let's say it.
I did say it.
Oh, good.
I did say it.
All right, now stop. Now stop. The asymptote is that line that the graph is trying so hard to touch, and it keeps going closer and closer and closer to the asymptote. It's weird, I know. It's a weird word. It sounds weird. It's fun to say, asymptote.
Acid. I can't say it.
Asymptote.
Acetote.
No, not acid toad.
Acetote. My toe.
Your toe is made of acid.
Yes.
Okay.
Watch.
That line, which in this case is the x-axis, the graph is trying so hard to reach it. It's going to go all the way down to the end of the building, then it's going to go all the way to the furthest point of Pasco County, and it's either going to try all the way to graph all the way to Tallahassee, and it still won't touch the x-axis, but it will be so close. The x-axis is the asymptote. Okay, now, if you want an actual definition for the asymptote, I'll write down the word. Asymptote. Asymptote. Everybody say it. Asymptote.
Acetote.
Asymptote. Everybody say that. Asymptote. So what it is? That's 3 times I'd have to go shh to get you guys back. What the asymptote is the line, copy this down, the line that the function is trying to reach but never will.
How do you say it
The
again?
line of the what?
Another way you could say it is the line that the function is approaching, but never actually meets.
Can you write?
Bro.
The line that the function
What's the function?
approaches
It's part of the line.
Why is your y so big?
but never meets. Bo and Jacob, stop. The line that the function approaches, sorry, my handwriting, but never meets. No matter how hard it tries with all its might. Okay. Can I erase this? Now I want to play the video. You do not have to take notes during the video. We will take notes after the video is over when I like break it up into like little pieces.
Both exponential and linear equations are two very fundamental concepts in mathematics. And in this video, I'd like to discuss the difference between the two. And in this purple or pink equation here, you can see y is equal to 2 to the x power, where the variable is the exponent. And when the variable is the exponent, you have an exponential equation. So that's this curve here. And essentially, every time you increase x by 1, the y value is multiplied by 2. So you can see that pattern with any exponential function, where as x increases by 1, the y value multiplies. Or in this case, the y value multiplies by 2. And when we look at this linear equation, you can see this y is equal to 2x minus 1, graphed in orange here. And the key point with linear equations is that as x increases by 1, the y value always adds the same amount. So as x goes up by 1, y goes up by 2. You can see that again here. As x goes up by 1, the y value goes up 2 units. And that pattern just keeps going forever along this entire line. And the fact that as x goes up by 1, y goes up by 2 is always related to this number here, this coefficient on x, which we call the slope of the line. But the key thing is that as x increases by 1, the y value increases by 2. Or at least in this case, it increases by 2. But in general, for a linear equation, as the x value increases by 1, the y value increases by some fixed amount. So for this one, we could say as x increases by 1, the y value increases by 2. So another way to think about these two different types of equations is that I view linear equations as additive equations. So essentially, every time x increases, the y value is added to. In this case, we're adding 2 to each y value. But when we're dealing with exponential equations, then with these, I think of them as multiplicative. And I say that because every time that the x value increases by 1, the y value is multiplied by some certain amount. In this case, it's multiplied by 2.
Okay,
If you're a freshman looking for a perfect place to study,
I want everybody to write down in their notebook silently. If anybody talks, you get out, okay? You're going to silently write down the main difference between the exponential function and the linear function, or exponential equation and linear function. He just said it and explained it in detail, and I noticed that most of you thought that watching this video meant you could zone out and look at your pencil, or look around the room, or look at your shoe. I noticed that. It's very sad that you guys will pay lots of attention to your phones when you can scroll social media, but I put on a 2-minute video and you can't pay attention for 2 minutes. So write down the main difference in your own words, or you could literally write it in 2 words, the main difference between the exponential function and the linear function. And if you can't put that into words, write down one thing that you learned from that video. One thing. And if you can't do that, simply write, I did not pay attention to the 2-minute video. That's all you have to write. Very good. I'll give you that. Stop writing what you wrote. Okay, let me see what you wrote. No, don't say it out loud. Write it down. Shh. Nothing? You were the one that I was looking at was going like this to your pencil tip. Anything wrong? You don't know? Okay. Anything? You're like a quarter of the way there, but that's okay. I can tell that you were trying to listen. Anything? Anything? Did you learn anything from the video? I can't read what that says. Did you learn anything, or is that something from before? I'm gonna give you that, even though that is a.
Am I wrong?
Red,
Yeah,
not
I'm
wrong.
wrong.
Oh yeah, forgot. Hey, where'd that Snickers go? I had Snickers in here. You stole it. I don't have any chocolate. I'm sorry. I owe you a chocolate. Just remember. I don't remember.
Oh, yeah, I'm trusting you.
That's all you got out of it? He was not talking fast.
For real.
That is not totally correct, but I can tell that you were paying attention because you had been at the church up something like that. That's not totally correct, but I can tell that you were paying attention, and that's really all I care about. I'm gonna go over it. Okay, too late.
I've been reading my hand for
Oh gosh. No. Okay, guys. I feel like teaching in this day and age is really, really difficult. I'm not going to go into a little speech about it, but it's really difficult because you guys are so overly exposed to so many other videos and things like that. It's not necessarily your fault. That's the time that you live in. I didn't have that when I was younger, and so just watching you guys like go through school where you can barely even pay attention for like a minute is very scary. You guys have to overcome that. Fewer screens at home, more paying attention at school. That's just my advice to you, and I'm gonna move on, okay? Otherwise you will not make it in life if like you're just like, I need constant stimulation, and you can't like watch a 2-minute video and get anything out of it, okay? I'm just gonna back up. I wanna go to the beginning of the video because I wanna talk about what he just said. And for those of you who weren't listening, It'll be like the very first time.
When I was accepted to SU,
What?
one of the greatest days of my life.
Okay, just remember right now, Bo, I have a class to teach, okay? Okay, so what I'm gonna do is I'm gonna scroll to this, and I'll just very quickly go over the answer to the question that I asked. The main difference between the linear function and the exponential function is, you could have literally written down that the linear is a straight line and the exponential function is curvy. I would have been okay with that. But what he specifically said is that as x increases by 1, the y value increases by 2. And he specifically, after that, then he wrote down that it's additive, meaning you add 2 to the y every time, and then he drew a picture that showed that if x increases by 1, meaning you go from 0 to 1, then the y value goes up 2, which means add 2. If the x value increases again by 1, which means the x value is adding 1 again, then again it's going up 2, adding 2, and again and again. Every single time the x value gets added by 1, the y value gets added. It's additive. Now, the number 2 is just specific to this equation because it has a slope of 2. But a linear function or linear equation, because of the slope and because of that perfectly straight line and that slope that stays consistent, is being added every single time. Now, then he said, on the other hand, the exponential function is multiplicative. And if you didn't write multiplicative on your notebook, that would have been fine. If you said like the linear is when y is being added to, and the exponential is when y is being multiplied, that would have been fine too. Or if you just wrote addition and multiplication, I would have been okay with that because it would have showed me that you were paying attention. But very few of you were. Okay, so over here, we see that this curve is shooting up so quickly because every time, we'll start with this point right here because these points are a little bit harder to see because they're so close to the x-axis. Over here, 0, 1, the point 0, 1, right here, when it goes to the next point, which is 1, 2, it's going over 1, so add 1 on the x, and then it's going 1, and then 1, 2. So then it looks like it's going up 1, right? So it looks like it's being adding 1, just like the additive over there. But when you go again, add 1 to the x, and then you go up 1, 2, now you're adding 2. That doesn't make any sense. And then it goes way up. You go over again and it's going 1, 2, 3, 4.
Multiply by 2.
So add 4, that doesn't make any sense. So it's not really adding 1, it's multiplying by 2 every time. And I'll show you that much more clearly when we do a table of values, which is what I'm about to do next, okay? So the main difference is that the linear equation is additive and the exponential equation or function is multiplicative. If you didn't write that down yet, write it down now. Now remember, the fact that it's being multiplied by 2 or increasing, adding 2, the 2 part is just specific to these very specific numbers in the equation. But in any linear or an exponential equation, it will be addition and multiplication.
So if it's like 5 to the x power, then multiply by 5.
All right. So I'm gonna go, I posted this on Canvas already, so if you need to copy down anything from here or rewatch it because you weren't paying attention, you can do that. All right, so I'm gonna just get back to this like beginning screen because what I wanna show now is what it looks like to actually graph a linear equation compared with an exponential equation or function. Now, we know how to graph linear equations the easy way, right? When they're in slope-intercept form, so easy. You just grab your, y-intercept, thank you, and you plot that, -1, boom. Then you grab your slope and it's going up 2 over 1, up 2 over 1, up 2 over 1. Yay. Now, do we have those types of like hints in here?
Nope.
No, we do not.
Oh.
So we can't graph it the same way. So we're gonna graph both of them using a table of values. And that's a fancy word for just saying an X and Y table, where we're going to choose our inputs and see what comes out, okay? We get to choose anything we want to put into this machine. So since I can choose anything I want, let me think.
Unicorn.
I'm gonna put a unicorn in
Chicken.
and see what
Snickers.
comes out.
A chicken.
I'm gonna put in 86,291.6622222299999884.
Say
Chicken.
that number one more time.
Yeah, write that down because that's what we're gonna put in. Because that'll be really fun to graph, right? Since I can use any value. No, that won't be fun at all. If I can choose any X values I want to graph, what's a good one to choose?
1.
2, I love that, yeah. 3. 3 is good. 1's great.
0.
0's the best.
No.
Woo!
Bless you.
I
That's
can't
a
even
good
put a
value.
sneeze.
That's a good value.
That's a good value. I'm gonna input a sneeze and see what comes out. Okay. Everybody calm down. Okay. A good rule of thumb for deciding what your inputs should be is basically choosing a couple of really, really easy numbers that are close to 0 and 0. So what I would choose are -2, -1, 0, 1, and 2. And you can go to 3, 4, -3, -4, that's totally fine. Also, remember we did table of values with our absolute value functions. To graph our absolute value functions, we did a table of values. Okay, now I could just put my y right here, but I'm actually gonna put this entire expression right here, 2x minus 1. So I actually have some space to plug it in, work it out, and then get my output, okay? So when I plug this in, I'll get 2 times -2 minus 1. Let's do that now. 2 times -2 is?
-4.
-4 minus 1
-5.
is -5. 2 times -1 minus 1. 2 times -1 is?
-2.
Minus 1 is?
-3.
-3.
Oh yeah, Bo.
2 times 0 is?
0.
Minus 1 is?
-1.
-1. 2 times 1 is going to get easier. 2 times 1 is 2,
1.
minus 1 is 1. 2 times 2 is 4, minus 1 is
3.
So right here, we have all of our coordinate pairs. That would be super easy to graph. I've got my -2, 5 down here. I've got my -1, 3. You guys see where I'm grabbing these coordinate points? My x and my y value, that's a coordinate point. This is what I put in. This is what came out. Together, they make a coordinate pair or point on the graph. And then I have -1, -3. And then I have 0, -1, and then I have 1, 1. Then I have 2, 1, 2, 3, and then I could keep going. but I won't. Another thing I want to take a look at with our function table is notice that it was very good to choose values that just kind of increased by 1 to keep things nice and steady, right? So when we increase our x values by 1, we'll be able to see the pattern really easily of what's happening to the outputs, what's happening to the y. Okay, so going from -2 to -1, how is the x value changing? From -2 to -1, how's it changing? Adding 1, good. So +1, and then from -1 to 0, adding 1, and then from 0 to -1, adding 1, and from 1 to 2, adding 1. Okay, let's see what's happening over here. To go from -5 to -3, what's happening?
Adding 2.
+2. To go from -3 to -1.
+2.
To go from here to here,
Adding 2.
and from here to here.
Adding 2.
Right? And that is additive, right? Because we're adding the same number every single time x increases by 1. Y increases by the same number. Not the same number as x, the same number as y, from 1 to the next. Okay, so this, just showing this table without graphing, proves that it's linear because it's increasing or adding the same number every single time, okay? Now, we're gonna do the same thing over here for our exponential equation. So I'm gonna grab some x values. Shall we do the same ones?
Yes.
But it's an exponent. Well, let's get crazy. Let's we can make x
2 to the
anything. What
fifth
about
power.
64,228? No?
Four
Can you even do it
million.
on a calculator? Yeah, let's just do the easy ones.
0.
-2. -1. 0. 1. 2. This will also allow us to see what is y doing from one value to the next when x is increasing by 1, right? Because it's still increasing by 1 every time, right? Now I'm just going to put in my 2 to the x power, and then I'm going to get my output. Now remember, we're plugging in our x values, our input values, to this little exponent here. That's different for us. So you have to be really, really careful and make sure you're plugging this number into the right spot. -2. Now, even as I was saying that, I was just about to write -2 right here.
2 to the negative second power.
2 to the negative second power. Break that down for me. What do I do?
-4.
No!
Brother.
You hear the last two
Take the
beats?
calculator, you go boom, boom, boom.
Carmine.
Isn't it like 0?
Nope.
0.25.
Oh, wait, it's like.
What
It
is
is.
it? You did it on a calculator?
Bum, bum, bum,
Oh no,
bum,
Grayson, I believe you, but I didn't want you to do it on a calculator. I wanted you to use the properties that we've been working
I'll
on.
use my brain.
Okay.
1/2 squared, which is
Very good. It's 1/2 squared because it's got a negative attitude. We send it to the basement, and that would be 1/4. What about -1? 2 to the -1 power. What's that? Lily.
2 to the -1 power
Were you paying attention to the one we just did when we had a negative exponent?
Oh.
You gotta pay attention, okay? We just said that when the exponent is negative, it's got a negative attitude, so it goes to the basement, remember? So what would that be if this has got a negative attitude? It'll be, guys, Faith? 1/1? 1/2 to the 1 power, which is simply 1/2, right? Yeah. Now it's gonna get easier. What's 2 to the 0 power?
0.
1.
It's 1.
Remember the properties, people?
It's
Remember
1.
the
It's 1. I said 1. I said 1. I said 0.
2 to the 1 power, 2,
When I get to get that on.
and 1 2 to the 2 power, or
Why would you get that wrong?
x squared is 4.
And you thought you get that.
Okay.
You.
Now, real quick, remember how we were going from this one to this one to this one, and we saw that they were being multiplied times 2? We can see that again. I'll start from this point again for now, and go from 1 to 2. We saw that you could say, well, isn't it increasing by 1? And then when you go to the next one, you see, but that's not increasing by 1, so that doesn't make any sense. So if we say, well, it could also be, 1 could be multiplied by 2 to get 2. Do you mind? And then we see that that's consistent with what's happening here. You could also throw in one more input, put one more thing in, or you can put as many in as you want, and then 2 to the 3rd power would be 8, and we can see that it's happening again. The y value is being multiplied times 2. We call this a constant ratio. And this is the telltale sign that we are looking at an exponential function when there's a constant ratio. Constant meaning happening over and over and not changing. And ratio meaning a fraction, but it's being multiplied by a fraction. And a fraction being 2 over 1. Yeah. A constant ratio meaning that it's, the easy definition would be, a constant ratio is when the y value is being multiplied. Anybody packs up, they're staying after. The y value is being multiplied by the same number to get to the next value. That's kind of the easiest way I can describe it. Now, if we jump backwards here, let's just test to make sure that 1/4 to get to 1/2 is actually being multiplied times 2. 1/2 times 2.
2 over 2.
Wait. I'm sorry, 1/4. I meant to say 1/4. 1/4 times 2 is 2 over 4, which is 1/2. So that is being multiplied times 2. Let's check this one. 1/2 times 2 over 2. 2 over 1.
2 over 2.
Which is
1.
1.
Yay!
Which is what that is. 1/2 times 2 gets to 1. So we can see the constant ratio. Do you guys see that? And then all of these points, if you look, this -2, and then -2, and then positive 1/4. If you go even back further, and you go to -3, what is it gonna be?
Not even
It's not touching, but what's the y value gonna be?
Very small.
Can anybody
Oh,
do?
1/8.
1/8, very good.
Then 1/6.
1/16.
Then 1/30.
1/30.
He deserves
1 over
32.
32.
He deserves a piece of candy.
1/28.
He deserves a piece of candy.
Please let me handle that. Okay, I don't need that.
I'm so sorry.
Okay, I think this is all I want to cover with you guys today, so, yeah, you guys can go.
That's it.
That's it for today.
No.